So again, this should be something we've seen before, just may have been a minute since we talked about the imaginary number, because I'm not sure how long ago you took Algebra 2, which would have been the main time you would have talked about this. But the imaginary unit is what we get, the imaginary number, is what we get when we're dealing with complex numbers or when we try to take the square root of a negative number. So this right here is pretty important for us, that I is equal to the square root of -1 or I squared is equal to -1. That's going to be a huge little bit of information for us today in working with these complex numbers. But it is really important to make sure we know where it comes from and why we end up with an I sometimes. And that's what this first example here is going to kind of talk to us about. So we have the example, square root of -25. When you first learned to deal with square roots before you had your multiplication chart memorized. Yes, sir? There's another packet in there. You do the square root of, and then break down the number that's in here as much as possible. So -5 and then 5 times 5. So when you learned this back in the day, you said, 5 times 5, that's got a pair, so we can take out the 5. So we would have 5 times the square root of -1. And then we got stuck. So until we learned about the imaginary unit, we didn't know what to do with that square root of -1. You can't actually take the square root of a negative number unless you make it a complex number. Now this works backwards and forwards. So if we check our result here, this 5i, if we take 5i and we square it, exponent rules tell me that I'm going to basically distribute that squared to everything inside. It's not distribution. I should never use that word, but it kind of looks like distribution because this becomes 5 squared and I squared. Well, what's 5 squared? 25. And by definition that I've just put in a cloud up there, what is I squared equal to? -1, so 25 times -1 goes back to being -25. So these are inverse operations here that actually works, which is why we have both definitions, that I is equal to square root of -1 and I squared is equal to -1. That totally works. An imaginary unit becomes a part of what's called a complex number. A complex number has two parts, okay? This is what a complex number typically looks like, this right here, A plus BI. It has a real part, like a regular looking number, that's the A, and it has an imaginary part, the BI part. So you have real part and an imaginary part that make up an imaginary number. If the complex number itself has only the imaginary part, that's when it becomes just an imaginary number compared to a complex number. Okay? One of the things we're going to need to be able to do with these complex numbers is work on our operations with these complex numbers. We're going to spend a while here. We're going to add and subtract them and then eventually divide them. Adding and subtracting is really simple. It's really just classic good old combining like terms, CLT. Your like terms are going to be the things that are real, the parts of it that are real, and the parts of it that are imaginary. And it's really just that simple. So in part A right here, we're going to add the complex number 5 minus 11i to 7 plus 4i. Well, if we're showing our work here, which I will for this part, we're really just taking the real parts, 5 and positive 7, and the imaginary parts, negative 11i and 4i, and we're adding them together independently. 5 plus 7 is 12. Negative 11i plus 4i is negative 7i. And voila, that is the solution. That is the sum when you add those two complex numbers. See how it's just combining like terms? The I acts like a variable, but it's really the imaginary number. Same vibe if we're subtracting them, except that instead of in individual parentheses, you add them, you actually subtract them. So if I'm showing my work here, this would be negative 5 minus negative 11. I'm doing that on purpose. Just stick with me. Plus I minus negative 6. So the negative part essentially gets distributed to that second parentheses, but you're subtracting the like terms together. Obviously, minus and minus means plus, and after lunch, we'll finish this problem. Y'all go to lunch, we'll come back. Okay, right before lunch, we were working on this problem. We're at the point where we want to combine like terms, but we have negative and negative, which I know means positive, so we're really adding those numbers. Negative 5 plus 11 is 6. And then I plus 6i is 7i. Just as a heads up, handwriting wise, I find it significantly easier to understand what you're writing if you give your I a little bit of a tail. You'll notice I do that every time I write them, because otherwise you'll think it's a 1 or like a stray colon, I don't know. So if you curve your I a little bit, it does kind of help you understand what you're looking at. That's just a tip for the future. Correct. So I'm still subtracting. That's a good point. I'm still subtracting the second term from each pairing. Bless you. So I'm doing -5 minus -11, which would be what I'm doing here. So -5 minus -11, and then I minus -6i. But complex numbers generally have a plus in between them. So if we put the real part here plus the imaginary part here. If you're like, honestly, that didn't make any sense, part 2, what else you could do is just distribute this negative first and then act like it's an addition problem. That is also fine. Okay, so you can also do that. On to the back we go. So that was adding, that was fine. Here's why we reviewed foiling at the beginning of class, because when we're multiplying complex numbers, it is essentially a double distribution or a foiling question, except that when you combine like terms, you get an additional step because we're working with complex numbers. Let's take it easy though first. Let's say we just have a single distribution, 4i multiplied by 3 minus 5i. It is a classic distribution problem, so we will multiply. 4i times 3 is 12i. So you multiply just like normal. And then 4i minus 5i, or multiplied by -5i, I guess I should say, is -20i squared, right? Same way x times x is x squared, I times I is I squared. However, your spidey senses shouldn't be tingling because what today did we learn we can change I squared to? -1. So when we come down here to show our next line of work, it would be 12i minus 20 times -1. Which changes the sign of 20. So when we write this answer, it should be 20 plus 12i, because -20 times -1 is positive. We generally put the real part first and the imaginary part second. It's not wrong technically if you write 12i plus 20, but I don't like it. So let's put the real part first and the imaginary part second. Cool? Then we get into a complex number times a complex number. This is a FOIL question. Just like we did at the beginning of class, we're going to multiply the firsts together. This is -14. The outsides together, this is -35i. The insides together, that's +6i. And the last terms in each parentheses together, that's +15i squared. That looks like regular FOIL, yeah? I know the squared's at the back instead of at the front, but it followed the same process. Here's the things I noticed, 2 things at once. Number 1, I see that we have like terms in the center. I also see that we have I squared again right here. So I'm going to do 2 things at once. I'm going to combine my like terms in the center. -35 plus 6 is negative, not positive, -29i. And I'm going to change that I squared into -1 again. Did I lose anybody on that step? Okay. At this point, we just need to finish cleaning up the steps. Since we got rid of the I squared, the squared term, since I squared is -1, that means we need to finish cleaning up these real numbers, because now that +15 is now -15. And -14 minus 15 is -29. So this complex number that results from multiplying 2 other complex numbers is -29 minus 29i. Feel okay? Up to now, adding, subtracting, and multiplying, generally speaking, with complex numbers, it's okay. It's division that gets a little crazy. When we divide, we're going to have to use what's called a complex conjugate of our complex number to be able to do that division. A complex conjugate of a number is literally just the opposite sign. So if you see here, we have a plus bi. Its complex conjugate is a minus bi. and vice versa. So you just switch the sign of the imaginary part. When you multiply two numbers together that are complex conjugates, two complex numbers, you end up back with a real number. Does anybody recognize this pattern? Maybe from like algebra, algebra 2? It would eventually make a quadratic. Maybe let me write it like this just to give you a reminder. Does that look familiar to you? Difference of two squares, yeah? If we remember the difference of two squares pattern, we get to take a shortcut. If you don't remember the difference of two squares pattern, you just get to FOIL twice. So it's really not a big deal if you don't see it, but it does make it significantly easier. Because we want to make sure that we end up with the correct complex number, when we are dividing them, we will multiply the top and bottom by the complex conjugate. And I think that's written here in these words, so let's highlight that. I can't reach that letter. By multiplying the numerator and denominator of the division by the complex conjugate of the denominator, we will obtain a real number in the denominator and thus be able to find the division quotient. So for example, if we are trying to divide 3i divided by 4 plus i, we are actually going to multiply the top and bottom by the complex conjugate 4 minus I times 4 minus I, or divided by 4 minus I. Multiplied on top and bottom. This means that we are going to have a distribution problem in the top. 3i times 4 minus I. And a double distribution problem in the denominator. If we take care of that numerator first, it's just regular distribution, that'll end up being 12i minus 3i squared. And I'm going to leave it like that just for now. I know you can probably see what's happening next. In the denominator, this is the difference of two squares that I'm multiplying together, which if you can take the shortcut, what that means is you square the first terms, 4 times 4 is 16, and you multiply the last terms. I times negative I is negative I squared. The reason we get to skip the middles is because they eventually cancel each other out. You'd end up with positive 4i and negative 4i. If you don't remember that, again, if you just straight up FOIL, you get to the same place. Okay, what do we see? Oh, wrong color. What do we see here? Negative 1. So we're going to take both of those terms and we're going to change them to negative 1. So we have 12i minus 3 times negative 1 over 16 minus negative 1. Okay, well that's just some regular computing. Negative 3 times negative 1 is 3. So I have 3 plus 12i. And then 16 minus negative 1 is 17. This is actually an okay answer for me, but your textbook will also sometimes write the answers splitting that denominator to both the first part of the numerator and the second part of the numerator. I will accept either of these because they are mathematically equivalent. I prefer the top one, just personally. That's personal preference. No reason. But do you see how I just split the denominator to both? Questions, comments, concerns about this division problem? Because the next one gets a little crazy. Can we try another one? On the back page. Okay, now we're going to divide 7 plus 4i divided by 2 minus 5i. So if I go to start doing that, I know my first step when I'm dividing these complex numbers is to multiply by the conjugate. What should I be multiplying by on top and bottom? 2 plus 5i. So it's the complex conjugate of the denominator, since we want the denominator to become a real number. Okay, so we're multiplying 7 plus 4i times 2 plus 5i all over 2 minus 5i times 2 plus 5i. We distribute along the top. I'm going to show all the work here. Because this is a double distribution, we'll end up with 4 terms at first. Then we can simplify them down. 7 times 2 is 14. 7 times 5 is 35. 4 times 2 is 8i. And 4i times 5i is 20i squared. Did I lose anybody doing that part? Which is a double distribution that I did rather quickly. We can do the same thing on the bottom. You double distribute if you don't see the pattern. However, this is a difference of two squares pattern. So I square the first thing. 2 squared is 4. 5 squared is 25. I squared is I squared. We can see here there are like terms in the center, and I also notice that there are 2 places where I have I squared. So let's take care of all of that business in one fell swoop. We'll end up with 14 plus 43i plus 20 times negative 1 all over 4 minus 25 times negative 1. Both of those last terms now just basically change signs. That means I'm having 14 minus 20, that's negative 6. So I'll do negative 6 plus 43i on the top, and then 4 minus negative 25, which is 29. So that is an acceptable answer, or we can split it into 2 fractions. Negative 6 over 29, let me write that number again, 29 plus 43 over 29i. Both are acceptable. Comments, concerns, questions? Are we okay? Okay, example 5 starts us on working on roots of negative numbers. And for the most part, this is going to be very familiar to you, because if you know your times tables and you know your perfect squares, easy peasy. Like, let's say I ask you, what is the square root of 81? 9. What is the square root of negative 81? 9i. Here's how we got there if you don't know it right away. We can split negative 81 into negative 1 times 9 times 9. That's the breakdown of 81. If we were to make like a tree, it would break down like this. Anytime there's a pair inside your parentheses like that is a perfect square. I recognize 81 as a perfect square. So we can go ahead and take the 9 out and have square root of negative 1 left over. And the square root of negative 1 is I. If you can go straight from negative square root of 81, or square root of negative 81, sorry, to 9i, that's fine. But we might get numbers like negative 75 that we're going to try to find the breakdown for. So we do need to start figuring out what numbers would multiply to make negative 75. I know negative 1. What's another set of numbers that would multiply to 75? 5, 5, and what? 5. Too many 5s? 5, 5, and something, though. 15 and 5? Okay, we'll go there. So 5 times 15. Can one of those numbers break down again? 15, 5, and 3. So here we go. If I do this, is there a pair of numbers? They get to come out. Is there a negative 1? Gets to come out as an I, which means this reduces to the 5 that broke out, the I that broke out, and that square root of 3 that gets to stay right where it is. You might have done these before making a tree, if this looks familiar. So this is 5 and 15. This is 3 and 5. We're looking for pairs in the tree. That's what I just did. I just did it underneath the square root altogether. Okay, what about this last one? What if we have some computations to do underneath the square root before we start to simplify it? Well, we want to follow PEMDAS here, so we're actually going to multiply using that exponent. So 5 squared is 25. 4 times 3 times 7, if you trust me, is 84. And we would do 25 minus 84, which is negative 59. Okay, we need to finish writing this down as the root of this negative number. Can we break the number 59 down at all? I know it's negative 1, right, times something. Is there anything that multiplies to make 59? Thank you for pausing, because there isn't anything. 59 is a prime number, so it's only these two things that break down underneath the square root. So I know that the I gets to pop out, but that square root of 59 has to stay underneath the square root. And that's a simplified form. Does that look familiar to us? We've done that before probably, yeah? But let's say something we're maybe not as familiar with is combining these square roots with negative numbers in different ways. Why is this one also not got a white background? Here we go. So let's talk about operations. Because the product rule for radicals only applies to real numbers, multiplying radicands is incorrect. When performing operations with square roots of negative numbers, we highlight. Begin by expressing all square roots in terms of I and then performing the indicated operation. Otherwise, it will not work. So if you see this example here, this is the same problem, one side done correctly, one side done incorrectly. We're trying to multiply the square root of negative 25 times the square root of negative 4. Before today, you may have been tempted to do this, where you say, okay, well, this is the same index and radical. We can combine them underneath. But then what happens is that you end up making this a positive number and we get the incorrect result. So first things first, take the i's out, then you can compute the things with the radicals. Okay, so let's see how that works. For negative square root of negative 18 minus square root of negative 8, we would first take out the i's. So I know immediately that these can be reduced to I square root of 18 minus I square root of 8. To add and subtract radicals, they do actually have to have the same number in the radicand. So let's hope that we can reduce these numbers so that they have the same number in the radicand. I'll reduce it this way because I think that might be easier for you guys. How do you break down the number 18? 6 and 3. Can I break down one of those numbers again? 2 and 3. Is there a pair of numbers that can come out here? The 3. What do I do with the 2? Leave it underneath. Okay, let's do the same thing with the 8. How do you break down 8? 2 and 4, and then 4 is 2 and 2. Does something pop out? There's 2 2's, and then there's a 2 left over, yeah? At this point, since the radical is the same with the same radicand, so we have the same index and insides, we can actually combine like terms. So 3i square root 2 minus 2i square root 2 is just a single I square root of 2. What if I have negative 1 plus the square root of negative 5 squared? Okay, well, we know right away when we're dealing with operations with negative numbers underneath the radical, we're going to go ahead and take that I out. So this is negative 1 plus I square root of 5 squared. Now remember, when you're squaring a quantity, that does not mean to distribute that in the square inside because there's a plus sign. This means that we are multiplying 1 plus I square root of 5 times negative 1 plus I square root of 5 together. This is a FOIL question. But we've done FOIL already today, so we should handle it. Negative 1 times negative 1 is 1. Negative 1 times I plus square root of 5 is negative I square root of 5. I square root of 5 times negative 1 is negative I square root of 5. And then I square root of 5 times I square root of 5. Ooh, what is that? I times I would be I squared. And then square root of 5 times square root of 5. It would just be 5. Boom. So let's clean this up because we got a lot of things happening here and I want to make sure that I end up simplifying this correctly. Are your spidey senses going off right here? What can I change that negative or that I squared to? Negative 1. So if I start to clean this up, this is going to be 1 minus 2I square root of 5. Since there are 2 of them, I'm combining my like terms right here. Plus 5 times that negative 1 that came from the I squared. Well, 5 times negative 1 is negative 5, so I can combine that with the 1. This ends up being negative 4 minus 2I square root of 5. I expect there to be some questions about this one because we did a whole lot of algebra very quickly. Can someone think of a question they want to ask? Go back through the steps from start to finish. Is there a moment you're like, ooh, Miss Quigley, you lost me? That would be a good time to ask a question. Okay, let's try C. This time we're trying to divide these two terms on top by 15, but I see that there is a negative underneath the radical. So I know right away I need to change that to I. If I go ahead and do that, this is negative 25 plus I times the square root of 50 over 15. Well, let's break that number 50 down. Let's see if we can make that radical simpler. What are some ways to break 50 down? 5 times 10, and then 10 becomes 2 and 5. Is there a pair? The pairs of 5s with a what left over? 2. Okay, so then I have negative 25 plus 5 that just popped out, I square root of 2, all over 15. Here's why your textbook and why most mathematicians do like splitting this at the denominator. It's specifically for questions like this. If you're not super strong in your fractional arithmetic, this will probably help you. When we split this one to negative 25 over 15 plus 5i, 5 square root of 2 over 15i, do you notice that we can reduce those fractions down? Negative 25 over 15, those numbers are both divisible by 5. So how can I reduce that down? 5 and 3. And then again, 5 and 15, both divisible by 5. So that becomes 1, or just square root of 2, over 5, over 3. What am I doing? I. So this is why splitting it at the plus or minus sign in between two terms on the top might be helpful because the fractions get a little bit easier to reduce. You can actually reduce it from the long fraction up there. And since there's kind of a pattern to the i's and the I squares, we're actually able to compute, the last thing, the powers of i's. Oh, look at that typo. That's so embarrassing. Please ignore. The powers of I pretty quickly when they're really, really large. The little main idea here says that in general we can always simplify, LOL, an integer power of I to exactly one of the following 4 powers of I, and it lists them there for you. I'm going to give you an even better shortcut here. When the exponent I is greater than 4, we divide the exponent by 4 and use the quotient and remainder shown in the following examples. Instead of doing it by 4, here's what I think the easiest thing to do is, and this is how I always attack these problems. We're going to take I squared, which for us, we've always been changing those to negative 1s, and we're going to see if I squared is raised to an even number. If I squared would be raised to an even number, then that means that term is exactly equal to 1. If you have I squared, and that quantity is raised to an odd number, That's going to be equal to -1. Here's how it comes in handy. If we wanted to write I to the 27th power by I squareds, how many perfect I squareds could I fit in to make 27? Basically, 27 divided by 2. 13. Do I have any left over? Right? 2 times 13 is 26. So I have one I still remaining after that. Yes? So I'm going to call this I squared raised to the 13th power times I. How did I get that number again? Great question. I'm so glad you asked. We took 27, we divided it by 2. The most it could be was 13 with 1 left over. Here's your 13. Here's your 1 left over. Well, here is I squared raised to an odd number. What is any I squared raised to an odd number based on what I told you? -1, which means this whole thing can be -1, and then we're going to multiply that by I. What is -1 times I? -I. So I to the 27th power is -I. What if we do that for 58? Okay. If we take I squared and we raise it to something to make 58, what would I have to raise it to? 29th, right? What is 2 times 29? 58. Is there any leftovers? No, that was perfect. What is any I squared raised again to an odd power? -1, and I'm done. I squared, or I raised to the 58th power is -1. You can do like the book suggests and like your notes suggest and divide by 4 if you remember all 4 of those things, but I found it easier to remember 2 things. That I squared to an even power is 1 and I squared to an odd power is -1. In general, for me, that seems to work better.